Welcome everybody. We are going to talk about some sin addition. Sin. No, that sounds like a really bad thing, but molecules do that a lot. So let's look at some of the primordial sins here, starting with osmium tetroxide. Well, that's one of the simplest compounds. This is a model. It's not at all in proportion because osmium in the center would be a huge atom and there'll be 4 oxygens attached to it. I'm showing this just to show you that it is constrained to do a sin just because of the structure. It has all these oxygens on the same side, which means it can only deliver on the same side. So let's say I have a pi bond, the same pi bond I've been touting around for the last I don't know how many days. So here's your alkene, and it can only deliver on one side, either a top or bottom. That's it. It cannot do a cross, anti. It has only choices of adding syn stereo specifically, just because the way the reagent is made. All right, let's look at it. Let's look at a mechanism with osmium tetroxide. Let's start with a chiral starting material this time. Let's say I have over here already a stereocenter. Let's look at what this chiral compound would do in the presence of osmium tetroxide. As we saw just a minute ago, osmium tetroxide can attack either from the bottom or from the top. Let's look at it. So in this case, you can have osmium tetroxide coming in from the bottom, and osmium, as I said, is a huge atom. And so it can spread over both of these termini. And so your pi bond here gets out. This is your nucleophile. Osmium here has got a +8 oxidation state, and it can grab those electrons. Osmium, as we saw here, is a +8. It can grab electrons. It's hungry for those electrons. So pi bond takes a step out, grabs that oxygen. Oxygen here is going to go to the osmium, and these pi bonds then step out and attack that carbon here. Now, there is really no regioselectivity the way the reagent is made. There's no adding on one side more than the other, because as we saw, the reagent was perfectly symmetric. So when the reagent is symmetric, the regioselectivity doesn't arise due to the reagent, like in the BH3 case. Here, it's going to go right at the bottom like this and add equally to both ends. So there's no really any regioselectivity between this end or this end. But it is stereospecific in that it can only add either from the bottom or from the top. There is no adding up here and down here or any which way. So it is very syn stereospecific. So let's draw a transition state for this before we go to the intermediate. So here it is. So you have a methyl group here that's going to get pushed up in this case, and you will have one getting pushed down when it attacks from the top. But let's look at one of them at a time. Pi bond is breaking and attacking an oxygen. The oxygen is breaking its pi bond and going towards the osmium. Those electrons go toward the osmium, and this pi bond then breaks and makes a bond with that carbon. That's a transition state for that. And let's look at the intermediate, and you would have an exact same transition state happening on the top, from the top of the molecule. And I'm not going to draw both of them because they're very, very, very similar. Now, after all of those electrons have kind of gelled, let's look at how it's going to look from a side view here. Here's your 5-membered ring, and in this case, your methyl's being pushed up. Here we have another methyl up, and you have your osmium tetroxide hanging on there on those monkey bars, doing its thing. So here you go. You have this oxygen, these oxygens coming down. We're also going to get attacked from above the plane, and let's draw that out here. So this methyl is not going to change. However, this methyl is going to change just because you are going to have attack from above. And so that's going to push that methyl down. And these are going to do like a flip on that monkey bar. They're like showing off. All right, so here's your oxygen here. Up, oxygen down. Now you can work these up. Now you do the workup with NaHSO3. NaHSO3, sodium bisulfite, is a weak acid. pKa is about 6.9, so it releases small amounts of acid. And I know this looks very simplistic, but Upjohn Company has got lots of papers on this, and it's a lot more complicated than this. There are instances where you have two of these on the osmium and so on. We're not going to get into that. Let's just say that in the presence of NaHSO3, which is slightly acidic, not very, slightly acidic, you're going to have some hydrolysis that gets that osmium out, and you would get the same stereochemistry preserved. So it's very stereo specific. So in this case, you are going to have up, up, and your hydroxyls are going to go down, down. And you're going to have hydrogens do that from the hydrolysis. Plus, you're going to have the counterpart. Now, can you call them enantiomers? What do you think? Are these enantiomers, diastereomers, same compound? What do you think, guys? What do you think these two are? Look at it. Hit that pause button. These two are going to be, well, diastereomers, because even though this part of the molecule is a reflection, this part cannot change. So therefore, when one of the stereocenters is inverted and the others are not, that's always going to be a diastereomer. So these are diastereomers. Just to let you know that there are really no rules that say you'll get a diastereomer every time. It really depends on the starting material. The symmetry, the regioselectivity depends on the starting material. A certain stereoisomer would only give rise to another particular type of stereoisomer. That's what we really mean by stereospecific. A certain type of stereoisomer gives rise to only a certain type of stereoisomer. Let's take, for example, a symmetric alkene. If you have a symmetric alkene like this, you are going to get, with osmium tetroxide and the workup, I'm just going to put OSO4, a symmetric compound. In this case, you're going to get OSO4 giving you hydroxyl both down syn stereospecific or both up syn stereospecific. In this case, you just flip this over, it's the same molecule. And it is a chiral center here. So these are meso compounds. So there's really no rule that you'll only get either diastereomers, enantiomers. It depends on the starting material. Let's say you have an asymmetric alkene. In this case, I mean, we're just sticking to 5-membered rings, but you could do open chain, any number of ring and carbons in the ring. I'm just giving an example, and let's say you add osmium tetroxide to this, you're going to get the same product as here, except with that methyl group up there. So you can have methyl up or methyl down, and you're going to have your hydroxyls always on the same side. In the osmium tetroxide example, they did not observe any anti-product. It was like 100% syn. Now, what do you think these two are? Well, obviously, they're not meso anymore. You don't have a plane of symmetry. Now, they're mirror images. You take this and you put a mirror here. You're going to reflect this over here. So you're going to have enantiomers. And in this case, as we saw here, if you take a chiral alkene, in this case, this is chiral here, you're going to end up with diastereomers. So I'm just going to write that down. Chiral alkene can give you diastereomers. So it really depends on your starting material. What kind of starting material you have decides what kind of stereoisomers you're going to get, if at all. All right, now that you got this, well, what's this NMO doing here? Do we need this guy? Yes, because osmium is one of those rare earth metals, so you can't really dump 1 to 1. You put a 1 mole % of this. Once you put a 1 mole % of that, that regenerates the osmium. So after your workup, you are going to get osmium breaking down into a osmium trioxide here. So that means it kind of got degraded. From +8, it went to +6. It got reduced. So NMO comes in, and that is this is morpholine, N-methyl morpholine N oxide, NMO, N-methyl morpholine N oxide. This is going to then give that oxygen over here and regenerate it. So you only need to have a 1 mole % of this. Let's say you have 1 mole of this, you just need 0.01 mole of this, but you should have an excess of NMO. So here, this goes in here. Well, eventually the osmium is going to grab that, and nitrogen here is positive, so those electrons move in and they will regenerate the catalyst. You are going to get N-methyl morpholine, which is neutral now, plus you're going to get osmium regenerated, rejuvenated, and ready to start the attack all over again here. So you go back to plus. So this is basically to regenerate the catalyst. So that's a really nice way of doing it. In fact, this is the most popular or effective way. You get more than 80% of this product, and they're all going to be syn. You don't get any anti. And the Upjohn company's got tons of material on this. The important thing is this is syn stereospecific because they only add on one side. It doesn't really discriminate between this terminal or this terminal like a BH would do. It goes on both. So it's non-regioselective. Most of the studies have shown it's just mostly non-stereoselective. You get mostly a 1-to-1 mixture. All right. Let's look at another one that's very similar. So I'm going to keep this and write this here so you can compare and see how similar they are. The other one is also heavy metal, bam, 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 KMnO4. Let's look at KMnO4 and see why it is a close cousin of OSO4. There's also RuO4, ruthenium tetroxide, and so on that can do this. We're just going to look at two. The reason why we're looking at this KMnO4 reaction is not because it's such a wonderful reaction. It's actually a very crappy reaction and gives a lot of mixtures, but it's the standard test for alkenes. So if you have a purple KMnO4 and you add it to an alkene, the whole mixture will turn kind of like a brownish at the end, at the bottom. Okay, so that's test for alkene. So if that happens, you know you have an alkene. So this is just a test, and you're probably going to do that in your lab. So why not just learn about it now, right? So you can just open this book and copy out that mechanism on your lab notebook. All right, let's go. All right, let's do a KMnO4 addition to alkene. I've been using mainly cyclic compounds. Let's do an example where you have an open chain. Let's say I have an alkene like this. A cis alkene, could have been trans. And let's say this is going to be 1, 2, 3, 4, 5. So it's pentuene. But since pentuene has a choice between E and Z, we got to specify what that is. So to do that, we cut the alkene in two like this. And at both termini, we assign priorities just like we do for RNS. So this is a carbon, this is a hydrogen, this is higher priority on that ladder, it's higher molecular weight. Same here, this is high, two highs on the same side, that's a Z. So you have a Z pin 2 in. Let's see what happens with KMNO4. Nice, beautiful purple. It's actually a lot deeper than this purple. Comes over, and it is going to be coming over cold. That's really very important. If you don't have cold, you're going to have that KMNO4 chewing up this molecule. So almost close to freezing. You don't want it freezing in a solid block, but maybe a degree or two centigrade. And you have sodium hydroxide in it, and that only comes in aqueous, otherwise it's a solid that won't react. So let's look at this. Let's draw it out. What does that look like? KMNO4 looks very similar to what you've seen a minute ago. It is the same tetra oxygen, and you have a minus, which is why you need that potassium. KMNO4 again is going to hug on to this alkene and do the monkey bar again. So let's do it. And it can go from this side or from the other side, both sides equally. So it's not regioselective and it's not stereoselective. It's really syn stereospecific. So this is your nucleophile. This is a +7 now. And so that's your electrophile. And nucleophile attacks electrophile. Same storyline, guys. We never change the storyline. We just bring in different molecules and do the same story all over again. It's just like in the movies. Every single story, it's got a girl meets boy, fall in love, make a bond, and move on. That's about the same storyline with molecules. They never get tired of it either. All right, let's look at this. And here, you can either have your methyl and your ethyl going in, and your hydrogen out, or you could have your methyl and your ethyl going out and your hydrogen in. And there's your manganate hanging on to those monkey bars, wiggling along. And let's draw the other attack from the other side, where your hydrogen is now on the dash, and your methyl and ethyl are on wedges. Same deal as before, same mechanism, same transition states, very similar to this, except you're going to have an manganese instead of an osmium, and you have a double bond here, whereas you have a single bond here. And there's the other hand holding on. So you have both of these intermediates here, and these intermediates that are fleeting. And these are mirror images, as you can see. Now your reaction's basically done with MnO4. If it is a really, really cold night, then you can have your sodium hydroxide come in and attack this and open that out. So this is going to go in, kicks this out. So that is going to do the same thing over here, but I'm just going to run with one of the enantiomers, and you know the exact same thing's going to happen to the other one. All right, so let's take a step over here and then draw this over here. Your hydroxyl hammered this in, opened it up, and your oxygen is now free. Your oxygen on this carbon is liberated from your manganese. Everybody else is holding on for the ride. Here's your hydrogens on the same side and your R groups are on the same side. You started with a cis or a Z, and you can see it's maintained. That's because nowhere here do we have a carbocation or a free swirling sigma. The sigma is always tied down by this manganese, and so you're preserving your stereochemistry here. It doesn't really go away all throughout. And now you have a hydroxyl and you have a manganate here. Your sodium's probably going to run around here and keep this company. Well, you added an OH and there it is. Now this oxygen can get protonated by water, but since this hydrogen's still right here, it's kind of tempting to do that. It depends on the concentration, but the main thing is it gets protonated. So you have water here, and that's another way to protonate that. And you have your oxygen protonated with the hydrogen. And that's going to release that oxygen here. Now manganate has got 2 anions on it. When you have too much charge, that's not a good thing because charges, are pushing and shoving to get more space. So something's going to kick out something here. And that's what it's waiting for. And this can come back here. And well, one of these can open up, come back and kick this out. I'm just going to put this like that. And you are going to have a very beautiful syndiol. Because you have both hydroxyls on the same side. So here is an oxygen. Now it is a negative charge because the sigma bonds became a lone pair over there. And you have a hydrogen here. Now this is going to become reduced because you lost oxygens. This is going to get protonated. This can get protonated with water. You have plenty of water in here. So you are in sodium hydroxide. So this is going to get protonated here. And it's going to give you a beautiful syndiol. And again, apologies for squeezing this in here. You have 2 hydrogens that are protonating the oxygen. Your KMNO4 is going to be first KMNO3 and then it falls off as MNO2 eventually. So that's kind of the story here. KMNO3 then falls off as MNO2, a brown solid. So that's the test. A nice, beautiful purple KMNO4 goes to like a brown mixture at the bottom. And this happens instantly. As soon as you keep adding the KMNO4, it's going to go down and you swirl it a bit. It's going to go turn a brown color. Then you know that's the test. Okay. Now this is really nice and you have cold. The risk with this is if your temperature goes up, you're going to oxidize this and lyse this, both the bonds. You're going to break the sigma and break the pi, and you're going to get a carboxylic acid on both sides. So you're really going to oxidize that to the maximum level if you have warm KMnO4 and sodium hydroxide. So warm KMnO4, I'm going to put warning. This is your Surgeon General's warning. Hot KMnO4 is going to break that up and oxidize, lyse the bonds, lysis. Going to lyse the bonds and give you carboxylic acids. It's just going to put OH here and OH here. If you had a di-substituted alkene, you would get a ketone. If you have two R groups for this hydrogen, you get two ketones. So this is really not what we want. This is just a byproduct. So that's why cold is kind of key for this reaction. All right, so again, I just wrote this down to show you how similar they are. Both of them are adding on the same side. Both of them are heavy metals. Bam, bam, bam. They're too noisy. The neighbors want them out. So you have to hydrolyze them. When you hydrolyze them, you're attacking that center toxic heavy metal and getting it out in stages here. In the meanwhile, your oxygens get protonated and you're getting a beautiful syndiol. You will get this plus the one with this. So I'm going to put plus minus enantiomer's. The other enantiomer is going to be the one where you have your ethyl and your methyl going in, your hydrogens coming out, and your OH groups going down. So you will have a 1-to-1. Again, it's not stereoselective where one of the enantiomers is more than the other. You would get, let's say, A and B are going to be plus minus enantiomers, and it's a raceme because you're going to get a 1-to-1 mixture. There is no way you can have more oxygen here or versus here. They're going to be equal. So it's not stereoselective, nor is it regioselective just because you put both at the same time. You can't choose one end over the other end. However, you can choose the direction, which is why it's stereospecific, syn stereospecific. All right, guys, I hope you see the parallels between both of these reactions and how similar they are. We'll talk to you soon with more sense to commit. Bye.